Hi, I'm Mark Webb. I'm from MKW Ventures Consulting, and I'll be talking about flash memory technologies and costs through 2025. Some of the contents we'll talk about today are NAND companies and current status, next generation technologies and announcements that have been made, and some speculation on what might happen in the future, a model for cost reduction on NAND technologies going forward, relative die costs for all the current manufacturers on all the current chips they're shipping, and what we project for the future bit costs through 2025, and then an ASP versus bit cost model on some of the challenges there. So NAND companies and their current status. So the 96 layer generation, which is 92 to 96 active layers, is a dominant technology today. It's ideal for 512 gigabit. It works for 256 gigabit, and it's capable of 1 terabit plus. And one of the key things here is that we don't need new amounts of layers in order to get a higher density. That's not the push right now. The 96 layer is greater than 50% of the bits shipped today. The 128 layer generation, which will be 112 through 144 active layers, is being introduced now. It's going to be less than 15% of the bits in Q4 2020. So while it's been announced by many people, there's lots of comments on it. There'll be comments at this conference. That's still going to be a pretty minor bit contributor at the end of this year. 176 layer generation, which is 160 to 192 actual layers, is being announced and developed. And then a 256 layer generation is possible by all companies with no limit. So we'll keep adding more layers, and there's no current limit seen. Note, again, we're doing new technologies for lower cost, not capacity, and that'll be important when I talk about my cost slides. So company updates. Samsung is moving to 128 layer now. It's still one string stack. This is actually quite amazing. Everybody else has gone to dual string stack, but Samsung has been able to stick with one string on there. So there's no, it's all done at one edge and one contact hole. No no CMOS under the array yet is shipping. So this is important because this is something that they'll implement in the future, but right now it's not being implemented, and it does provide over probably about a 15% die size savings. Hynix is moving to 128 layer, two string stack. It's CMOS under the array. They call it PUC, periphery under cell. WDC and Kioxia are running a 112 layer, two string stack. We do expect at least some of the products will have CMOS under the array. Micron is in a very different position. They're doing a limited ramp, or they've announced a limited ramp on 128 layer, two string stack, CMOS under array on the first generation replacement gate. Replacement gate means charge trap technology in Micron's case. Micron previously been running floating gate. They're moving to charge trap flash now, like most of the competition is. And as a result of this, we expect to see minimal cost reduction expected over 96 layer in the 2020 and 2021 timeframe. And this is simply because they're ramping new technology, new tools. They have a lot of conversion costs. So it's going to really kind of hold them back. Intel is moving to a 144 layer floating gate, CMOS under the array, and I'm guessing here that it's a three string stack. I'll look to Tech Insights to provide data on what they see in their teardowns. So this is where the companies are today. There's another company I didn't mention, which is YMTC in China. They've been making a lot of announcements for many years at this conference and other conferences. YMTC is now shipping 64 layer wafer bonded X stacking technology. They plan to move to 128 layer. I believe they made an announcement around February. But in general, they tend to pre-announce things, so I wouldn't expect it to be ramping anytime soon because 64 layer is just ramping now. 64 layer product has excellent die size due to the CMOS under array provided by wafer stacking. So by doing that, they do periphery on one wafer, they do the array on another wafer, they stack them, so you end up with a very small die size, stacked die size. The problem with this is this technology is very expensive and very complex. It's seen as a way to allow periphery to be optimized, but it is not cost competitive yet. Our model shows that the costs are 50% higher than competition, and that's if they hit their yield targets and get to maturity. YMTC is still less than 2% of the industry bits shipped annually. And if they execute to plan, we estimate that they could grow to over 5% market share by 2025. So again, the key from last year is they are actually shipping some of these products. They have shown up in teardowns. However, the technology is very complex, and we'll see if they're able to go scale this to 128 layers. Future technologies, all companies have announced moves to 1YY, which I guess I'll call 176 in late 2021. And then 2XX, which would be like a 256 layer technologies are possible. With Intel's announcements of the Hynix sell-off, we expect floating gate to end, although a recent announcement by Hynix said that they would continue to run floating gate for another 2 to 3 generations. And this is primarily because Intel will be transferring the R&D from Intel to Hynix. So as a result, they already have some work that's in progress. One other thing that note, this came from IEDM papers last year, is a number of companies have actually experimented with floating gate for alternative architectures, but currently the only one still using it as of today is Intel. The 176 layer nomenclature is being used for the next generation. We expect companies to make a pragmatic decision on the number of layers based on yields and costs. We've already seen this with 128 layer. So an example is if you can make, say, a 160 layer technology cheaper or higher yielding or avoid issues than 176, you might choose that. If you think you're going to install tools and be able to get to 192, you might do that. You're going to make a pragmatic decision. There's no set number that they have to go with. With a 1 to 2 year cadence, I'm assuming about 18 months nominal, we expect companies to convert some, but not all of their NAND products on each new generation. QLC models. So I was not really originally a fan of QLC back in 2017, but it appears that the MLC TLC history will repeat itself on QLC. It'll start as a little bit cheaper with worse performance and endurance. We'll see few adoptions, lots of complaints. Performance, caching, and controllers will improve the product. Customers will become more tolerant of the issues, and it'll become dominant in bits over a 7 to 8 year time frame. We model that QLC bits are around 15% in 2021, and they'll grow to 50% of bits after 2025. It's theoretically 25% cheaper. Actual in our model is 20 to 23% cheaper after accounting for some design and test overhead costs. PLC, penta-level cell, is possible, and we could expect the same timeline if that came out. So again, if somebody introduced it, they have a chip, and then maybe 8 years later it crosses over and becomes 50% of the bits. The MKW Ventures model for NAND cost reduction. So going into the numbers I'm going to show you is each generation we assume that we're going to add about 30 to 50% more layers. The goal for each technology when those come out is to improve manufacturing efficiency. So the output per tool is the same, and the fab and tool vendors partner on this. So as a result, the goal is to have no cost adder for adding all those layers. In reality, we've added 10 to 15% to wafer costs for each new generation, depending on inputs from tool vendors. So we talk to tool vendors about what's possible and what the tool costs are and get input that way. String stacking adds to the wafer cost, maybe 5 to 10%. CMOS under the array adds to wafer cost because you have to do some complexity in building that. And again, that might be another 5 to 10%. On mature technologies, however, we assume 5 to 10% cost improvement per year. So if I just took a given technology, I give it to a fab, each year they're going to reduce the cost 5 to 10% just on wafer costs through efficiency improvements. One change this year, based on inputs from tool companies and from NAND companies, we significantly increased the wafer cost improvement rate on 3D NAND technologies. The end result is 3D NAND is becoming efficient at a faster rate than previously estimated. As a result, our cost improvements are improving in the model that I'm presenting. So here's a complex data. You can look at this offline, but basically this is NAND die cost, doesn't include assembly test costs for TLC or QLC NAND technologies. A through E are NAND suppliers. I don't give the names here. We can talk offline about what the names are and what the differences are between companies. And then it shows the cost for 2020, 2021, and 2022. And the key takeaways here: on each given technology, the costs go down every year as you get more efficient. In some cases, if it's mature, you still get some cost improvement just from ongoing learning. If it's a new technology like 128 layer this year, you're going to see a big jump in the first year in cost improvement because you get lower wafer cost, improved yields, and things like that. And then you can see that the next technologies, 176 layer and ultimately 256 layer, they're going to continue to deliver cost reduction. So right now, adding layers always reduces the overall bit cost going forward. Again, this is actually translated to bit cost. I said die cost, but it's actually bits for the NAND. And the key takeaway is bits keep getting cheaper. Now, I mentioned before that YMTC is doing a 64-layer technology based on X stacking. So if you look at this result, this is where I modeled the cost for in 2021 for YMTC 64-layer X stacking technology. And the key is that it's a very small die size, and this is assuming mature yields, but the wafer cost and the processing cost is much higher. And so as a result, they're really not competitive on cost. So what are the key takeaways from this? Costs are being reduced every year and with every new technology. We have exact numbers, company names, and reasons for numbers available for follow-up discussions. I don't want to get into all the details here. Each company has a different cost reduction path. And so each company will have either they're learning fast or they're behind. One interesting example here is that the cost leader at 96 layer is not the cost leader at 128 layer. In fact, they're modeled to have the highest cost at 128 layer. So the companies who's leading in cost and who is trailing in cost changes each generation. And then the other one is we have line of sight to at least 256 layers, and we will keep getting cost reduction going there. If I look at average cost trends for the next 5 years through 2025, I'm showing HDD cost and NAND cost. This is bit cost, and this actually includes assembly and test costs for the technology. The end result is going to be NAND average costs will be below 2 cents per gigabyte after 2025. The cost reduction on NAND is 20% per year on average. This includes what we get from new technologies, plus what we get from cost learning as fabs become more mature and equipment gets more efficient. Plus it includes the effect of QLC percentage, which as I mentioned is going to ramp from about 15% to 50% over the next 5 years. NAND and HDD cost crossover sometime after 2033. If you look at this on a log plot, you can see this. And then the update is there was a presentation from Hynix saying they're going to replace nearline HDDs. If we had 100% penta-level cell and it was yielding at forecast, the crossover would only move into 2031. So again, nearline HDDs are going to be around for a long, long time, and they will be the dominant for the low-cost storage. And again, on this one, there's lots of data. You can contact me for numbers and log plots and things like that to make it clear. But again, it shows you what we're seeing on NAND cost, again, not ASP, versus HDD cost over the next 5 years. So the NAND market and ASPs, NAND market pricing recovered some in early 2020, but then since has struggled. Right now, NAND operating margins are minimal. Bit growth is unclear, but probably around 30% CAGR each year. And then the bit cost will drop 20% per year on average, as I mentioned. All these numbers add up to a very challenging financial model if prices drop greater than 20% per year. Historically, my model is you should focus on 20 to 25% cost price reduction per year. If we end up in this situation, the result would be a slowdown in new technologies and CapEx because companies would have to decide how fast they want to invest and how fast they want to ramp new technologies. So in summary, there's no end in sight for NAND technology progression and cost reduction. There's no major limiters to adding more layers. QLC improves cost and will grow to 50% of bits after 2025. NAND costs will reach 2 cents per gigabyte after 2025. The NAND cost leaders change over the next 5 years. And then costs are modeled across HDD cost after about 2033 if you include all technologies combined. Again, numbers, backup charts, company names, and reason for numbers are all available. Call us to discuss. And additional contact information is shown here. Thank you.